Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology, and I want to thank each and every one of you for joining me in the webinar today. It's a pleasure to have you in here listening in, and I hope that everyone's week is going very well. And as you know, this webinar is being recorded, and we will be sending out the recording later this week. So afterwards, don't worry if you don't get it right away, just sit tight and we'll send it by the end of the week. That way you can watch it again or you can forward it on to your colleagues. And so if you are listening to the recording, thank you for watching and looking forward to having you enjoy the show. So today we're talking about pipe sizing made easy, and what I'm going to demonstrate is an example where I'm going to go through it really quick. So you need to make sure that you're paying attention and watching carefully. And the reason why I'm going to go through it really quick is because I want to demonstrate how the default settings will actually take you through the majority of the pipe sizing process itself. That way, it's even easier because it's going to, by nature, save you many clicks along the way. Then, once I've completed the example, then I'll go back through it again and I will actually explain more clearly what I'm doing at each step along the process. So really, I go through the process twice. That way you'll be able to see it twice, and it'll demonstrate how easy it is to do. So that's what we're going to be talking about today. Before we get into things, just a quick review of where you can find information about our software. AFT.com is our website, and I always like to point people to the products menu to find our software overview page. And the software overview page is where you can find all of our primary AFT software product applications. So we have AFT Fathom and Arrow, AFT Impulse and Extreme. Fathom and Arrow are for liquids and gases respectively, and primarily for steady state flow modeling, although they do have a extended time simulation module for each of them. But then if you're needing to do surge analysis or water hammer or gas hammer, then that's where you would be using AFT Impulse or AFT Extreme for liquids and gases alike as well. And then each product has a number of add-on modules. Fathom has 4, Arrow has 3, Impulse has 2, and Extreme has 1. And so today, what we're going to be focusing on is the automated network sizing module for AFT Fathom, and there is a automated network sizing module for AFT Arrow as well. And so when I'm demonstrating the example today using AFT Fathom's XT or ANS module, the process and functionality and the interface for using the Arrow ANS module is exactly the same. So if you have Arrow but not Fathom, then this process applies to you because it's going to show you how you would go through and automatically size your system before gas piping with AFT Arrow. So the functionality is identical on that, and we like to try and make things as easy as possible in that regard. So with that, I'm going to go ahead and get started. So let me move this out of the way. And so this is our system that we're going to start off with sizing today. So I have 3 pumps here that are operating in parallel in this closed loop system. And we have a set of heat exchangers and control valves. And this part of the system is the primary loop. You know, maybe this is a initial design where later down the road, this is actually a expansion, which that's actually the story behind this particular model file that I built, where initially we're starting with the system that I highlighted in red, And then later down the road, we know that we want to have an expansion to the system in blue. Well, the thing is, if we only size the system in red and we're not considering the system in blue yet because maybe we don't have a lot of details on it, well, when we go to add on the system in blue, the pipes and pumps will potentially be oversized for the system in red to handle the additional capacity for the system in blue on our expansion. So the reason why the ANS module for automated pipe sizing is really helpful is because it makes it so much easier for you to plan for expansions or maybe retrofits of a system in the future. And so that's what I'm doing here is I am sizing both the primary system and the expansion at the same time. That way, when the expansion goes online, the pumps are already going to be sized appropriately to be able to handle it. Okay, so through each of my flow paths here, I have 1,400 gallons per minute going through each of the primary heat exchangers. And then through each of the flow control valves, I'll just open one up here. That way you can see what the input looks like. Again, it's flow control, 1,300 gallons per minute. So the expansion is a little bit less flow. I did that by design just so that it's a little bit different. So here we have 1,300 gallons per minute going to each of the C and D heat exchangers. And then, since this is a sizing operation, we're going to size our pumps at the same time. So each of my pumps are using the sizing option, and 2,000 gallons per minute is our design flow rate. So I've got 2,000 gallons per minute through each pump. Now, all of the input is fully defined. As you can see, I have a green status light in the bottom right corner of the interface, so I can run my model and get results. But here's the challenge. If you try to run this, it's going to give you this wonderful, beautiful, yet dreaded reference pressure needed message. What in the world does it mean? Well, it's really important to read. So if you read this, this will give you a basic idea of what's going on here and why the system is not able to be solved. If you click on the help menu, which I'm going to give you all a homework assignment, and I highly recommend that you do this, it will take you to our help file where you can read about the role of pressure junctions and how they work. This topic right here is found in the main help file under fundamental modeling concepts and then role of pressure. This is absolutely critical for understanding with being able to use our software effectively, because many times people stumble into these potential mouse traps because they haven't taken the time to study how the software works. So essentially, what this message means is what is going on right here. Basically, in my big, gigantic, which is not that big, closed system, I have a portion of the system that is essentially bounded by fixed flow rates. We have essentially, let me go back to my model here. I have specified fixed flow rates for the pumps, and then fixed flow rates for each of the control valves. So Q is where I know what my flow rate is. So if we take this and we follow it around and we try to go through each flow path, we can see here that this is one flow path that is bounded by the fixed flow rates. I'll do it in another color here where when we split off this way and go down this path, this is another area where we are bounded by fixed flow rates. So that's why the system can't run, and the help topic will explain this for you in more depth. Now, don't just read this part, read the detailed discussion right here, because there are many other circumstances where you might run into this issue, not just using assigned flow junctions. You might have various combinations as you scroll down here with assigned flows and combinations of different pressure control valves where you might run into the same issue. And so this topic talks about what is going on, and it also gives tips on how to get around that. Incidentally, if you were to scroll down further to the examples section right here, there's a very special and important example that demonstrates this very well. It's this one right here, pump sizing and selection with control valves. FYI, if you don't have access to Fathom 12, you can still read the Fathom 12 help file, because now all of our help systems are on our website. So you go to aft.com, you go to the help site, and then pick whichever software that you're interested in. So without having a license, you could still get in and read the example. That way you can do some self-training if you want. So this example here has you do a very small scale of exactly what I'm doing, where I'm trying to size my pump and I've got these flow control valves right after it. You're going to run into the same issue by design with this example, and it teaches you a method of how to get around it. So what I need to do in order to get around this is I need to make a small change so that essentially this boundary condition here, where I know what the pressure is based upon the liquid level and the surface pressure and the elevation of where the pipes are connected, that tells me what my fixed pressure is here and here. So in order for this circuit of pressures to be able to communicate itself, we need to open up the flow of communication. So an easy way to do that, which the example of the pump sizing with flow control valves I just showed you will teach you how to do, is to take one of your control valves and set it to a constant pressure drop. And you want to have it set to at least a minimum pressure drop. And I'm going to set that to 10 psi, because you want to make sure that your control valve can maintain good controllability. So the minimum pressure drop for my control valves is 10 psi, and we need to do that with both of them. Now, the question is, when you're trying to figure out which control valve to set to a constant pressure drop, should you use this one or should you use this one? Well, when you're doing this, the thing to consider is which path is hydraulically more remote than the other. It looks like this path is more remote than this one, and in reality it is, but that may not always be the case. If this was actually like 20-inch diameter piping, then maybe this would be more hydraulically remote because it would have more pressure drop. So it just depends on what's going on in your system. So try to find the more hydraulically remote path and set that one to a constant pressure drop. And now we can run the model and we can get results. So that way it solves, no problem at all. And this is what our results look like. Now, I don't care about this because I haven't sized my pipes yet. So when you're doing this, you do have to go through the regular process of building your model and defining your input. But when you're defining your input, it's really easy, because I don't know the pipe size, so I'm just starting off with a guess. Steel and 16-inch diameter. So let me reset this here really quick. There we go. And make it a little bit larger. Perfect. Okay, so here in this example, we do have all of our pipe lengths defined, so that's fine. But as you can see, I've got a guessed size and material, and that's my starting point. And then we're going to automatically size this. Okay, so that explanation was necessary to just kind of open up what's going on here in our system. Now I'm going to do the automated sizing part. So make sure you're paying close attention because I am going to go fast, and that's on purpose, so you can see how quickly and easy it is to automatically size this system. So if you want to get out a stopwatch, feel free to time me and we'll see how long it takes. I think it's going to take 5 minutes. So here's what we do. Get ready, get set, go. All right, so click on the add-on modules button, and the first thing that we need to do is activate the ANS module, automated network sizing. And when you turn it on, we're going to use network, and so now we are good to go. All right, it is telling you that we have an exclamation point, but we're going to ignore that because nothing's defined yet. So we click OK, and now we have a new tab. So that's where all of the work is done, is in that sizing primary tab window. So here's how easy it is. I click on sizing. All of this that is set up as a default allows me to go right on to the next step. So that it makes it much easier for me. So now we're on to, sizing assignments. Which pipes am I going to size? I'm going to size everything. So I'm going to click on all, always include and weight, because I don't have cost information right now. So I'm doing a quick and easy sizing based upon the overall piping weight itself. All right, so I'm sizing every pipe in the model. Now I'm going to collapse my quick access panel. That way I have a little bit more real estate. And what we're going to set up here is some common size groups in this area here. I will talk later about what the heck that is. I'm just going to go through it really quickly here, and I'm going to move this over to the right side so that way I have some more space. All right, let me get this out of the way over here. Okay, so I'm going to click on new to give it a new name. So I'm going to create a group called main header. So I'm just going to call this main. And then I'm going to create another one called pump A. This is for the pump A piping. Pump, let me spell it right. Pump B piping. And then pump C piping. As you can see, I'm just creating more common size groups. Right now I have 4 of them. And then, so I got A, B, and C. This is going to be HXA. And then this will be heat exchanger B. And then heat exchanger C. And last but not least, heat exchanger D. So right now, before I do my automated sizing, as you can see, we have 35 pipes in the entire model. So if I just size everything like this, and I don't move any of these pipes into a common size group, I could potentially have 35 different pipe diameters on the workspace, which could lead to a really good design, but it'll make it a nightmare for the purchasing department. So we want to make it a little bit easier for them. So I'm going to force some pipes in the model to be sized, but they're going to have the same size. So here's how easy it is to set it up. Select it first on the workspace. So I'm going to select the pipes in my main header. Those are the pipes. Once you select them, you would go here and click on workspace to click on the workspace button, and that highlights the rows in the table. After we do that, we're going to scroll over and we're going to say move to Maine, not the state of Maine in the northeastern United States, the main header piping. All right, there's my little joke for today. And so now I'm going to go on to the next group of piping, which is going to be these pipes right here. This is going to go into the pump A group. So we'll click on workspace, move to pump A. So that's the pump A common size group. This is going to be pump B. So click on move to pump B. And then these are going to be pump C. So again, when you're moving these pipes on the workspace into a specific common size group, as the name implies, they will have the same common size. Hopefully that makes common sense. All right, so this group is going to be in the heat exchanger A group. And then these are going to go into heat exchanger B. And then these pipes are going to go into heat exchanger C. Again, all I'm doing is I am selecting the pipes on the workspace itself, and I'm clicking the workspace button. That way it highlights the appropriate rows, and I'm putting them into the common size group that I want them in. Okay, so now we'll reset the panels to how they are. And right now, they are ordered by pipe numerical order. This is not very helpful for me to read, so I want to click on this area here, and that will automatically sort everything by common size group. So as you can see here, we now have all these common size groups set up, just like so. And then there are a handful of pipes that are not in a common size group. So these particular pipes here will be whatever size they need to be, which is perfectly fine. But ultimately, I went from 35 independent pipe sizes down to 14. So that's going to make the sizing process a little bit easier for the solver. Okay, next step, candidate pipe sets. So this is where I'm going to specify what types of pipe I'm going to consider for the sizing. So I'm going to only consider steel pipe, 1 inch to 36-inch diameter. So what pipes are allowed to be used? Well, there's a whole list of them here, and I'm going to choose steel, and I'm only going to choose from standard schedules. So these are the standard schedules that I'm going to consider, and I'm going to add that to the list. I'm not going to add any other schedules right now, but I am going to select sizes less than 1 inch. I'm going to delete them, and then sizes more than 36-inch, I'm going to delete those as well. So all I'm considering here is steel pipe that is from 1 inch to 36 inches in diameter for standard schedule pipe sizes. And this set of pipe materials is going to be considered by all the pipes in the model. And so just like I did for my common size groups, I'm going to click on all, and they're all going to consider steel. All right, that's done. Now we're going to go on to design requirements. This is what drives your design, and it's how your pipes are going to be sized. So I'm going to start off with a new design alert, and this is going to be called 1400 GPM HX A and B minimum flow. All right, so the parameter is going to be volumetric flow rate, and it's going to be a minimum flow. If I get a little bit more, that's fine. I just want to make sure I'm not going less. Now, with this already being made, I'm going to duplicate it because I have another design requirement that's very similar. This is 1300 GPM HXC and D min flow. So this is the minimum flow that I desire through the expansion loop. And as you can see, it has all the same parameters. All I need to do is change the flow rate, and there we go. And then I've got one more design requirement. This is going to be my velocity. So 10 feet per second max velocity. Velocity is important to include because if I didn't add in velocity with this, then it would be possible for your pipes to all be 1/8 of an inch in diameter, potentially, because it's going to try and minimize the piping weight. But here, if you set a maximum limit on your velocity, then that will help kind of balance out your pressure drop to where your pumps won't have to work as hard. So now I've got my 3 design requirements. The question is, which pipes do these requirements go with? Well, you're going to set that up by assigning your design requirements to various pipes or common size groups. So here, the first one is going to apply to the group for HXA and HXB. So as you can see, it's applying to all the pipes in those 2 common size groups. And then next we have HX heat exchanger C and D. And then all of the pipes are going to have the velocity requirement built in. I'm going to set up one more design requirement, and that's going to be for my control valves, where my control valves have to have a 10 psi minimum DP. And so I set my name, and the parameter is going to be pressure drop. The minimum needs to be at least 10 psi. Now in this scenario, I only need to do this for 2 control valves. The reason why is because I already set control valves B and D to a fixed pressure drop of 10 psi. So those are inherently already meeting the requirement. So you don't need to check the boxes right now. Last but not least, sizing method. And so here we're going to do a discrete sizing, and we're going to let it suggest the best method. And now that that has chosen that option, we're going to go ahead and I'm going to save my model and we'll run it. All right, so I'm not sure if any of you were actually timing me, but I think it maybe took me about 5 to 10 minutes where I was talking through it, but I wasn't explaining all the various details. So here's what this is doing, is this is going through and it's trying to find a discrete size. That means it's trying to find a very specific nominal size and schedule that will meet the design requirements with a minimum piping weight. So what that means is I can't end up with some hydraulic diameter like 7.3 inches. It has to be able to come from a standard list. Now, what this is doing is it's running the model with the initial pipe size that I defined, which is 16 inches in diameter. So that's just my guess, and that told me that the initial design is not feasible. So with 16 inches in diameter, it calculated that the piping weight was 321,000 pounds, and because it was infeasible, that means my design requirements were not met. So after it did that, then it starts the sizing process. And it landed on an answer here. So we found that the best piping weight here is 245,000 pounds. We'll click on the output, and we can start to look at the results here. And I'm going to minimize this just to focus on one thing at a time. So let's take a look at the cost report. This tells you how much the overall piping weighs. 245,000 pounds essentially for the system. And so that's how much our piping weight is going to be. Now, let me look at the pipes that are sized. And this goes through and shows me the sizing distribution for all the pipes. So that's pretty nifty. Now, oops, sorry. My pipe size is 245,000 pounds. Let's see if we can do a little bit better and maybe drive that piping weight down a little bit further, because the less the pipe weighs, the less it's going to cost. So I'm going to go back to my sizing panel. And the only reason why I'm doing this is because I know that a different method will give some different results. So here, I'm going to use a different mathematical algorithm for doing my sizing process. And first, it's going to start with a continuous method. And while that's running, I'm going to explain what that is. So I talked about discrete sizing. That means that it has to land on a very specific nominal size and schedule. Continuous sizing means it can be any hydraulic diameter. So it very well could be 7.3 inches in diameter. So that's what continuous means. So the reason why I'm doing this is because if you start with the continuous sizing option first, that makes it a little bit easier to get a better start for the discrete sizing process. So initially my pipes are at 16 inches in diameter. So continuous sizing allows me to figure out, okay, which pipes are 12.4 inches, some might be 13.7, and that will be a better initial guess and a better starting point for when it begins the discrete sizing process. So what we see here is that based upon a continuous sizing for any hydraulic diameter that meets my design requirements, lowest cost or lowest piping weight is 216,000 pounds. Now look at this. My discrete sizing calculations are completed in just over a minute, and look at that. I now have a better cost, 241,000 pounds. So this just goes to show that when you're using different mathematical algorithms for the sizing process, it will potentially give you different results. So here I see a lower piping weight, 241,000 pounds instead of 245,000 pounds. And we're going to see a slightly different sizing distribution. So this is how you can see the pipe sizes on the output window. If we take a look at the visual report, this makes it a little bit easier to see when you put them right on the workspace itself. So I need to switch this to my output mode, and let me add my pipe length, and then make sure that my sized pipe nominal size is selected, and it is. So we'll show that, and there we go. So as you can see here, I've got 18 inches in diameter for the main header, and then for the pump A piping, 10 inches in diameter. And incidentally, we see that pump B and pump C actually end up with the same diameter, which is good. It makes our pump piping a little bit easier to procure. But we could have had slightly different sizing, and that could lead to a maybe better design. And then we have 8 inches in diameter for the A path, 10 inches for the B path, so on and so forth. So that is our pipes that are sized. Now, basically, I'm done. Well, almost. The next step is where I would create a child scenario. I'm going to call this scenario sized pipes. And what I want to do is I want to take the resulting pipe sizes here, and I want to convert them to input. All you need to do is click on the thumbtack right here, and that will transfer both your calculated pipe size and calculated results to your input. And so now when I go in and I reload the scenario, then this shows you what the pipe sizes are throughout the workspace. Okay, so now that I finished that and I went through really quickly, I'm going to go back through and I'm going to explain in a little bit more depth for each of the sizing panels what I'm doing to go through a little bit more detail here. So I'm going to go back to my original base scenario, and I'm going to delete my child scenario, and I want to set things up like they were in the original state. So I'm going to go through here and I'm going to delete my design requirements. That way I don't have anything set up. I'm going to delete my candidate sets, and I'm going to take all my pipes and set them to be not sized, and I'm going to delete all my common size groups. All right. And so this is just like it was in the case where I don't have any sizing parameters set up. And I'm going to turn that off. And there we go. Okay, so here's my starting point again. I have 16 inches in diameter for all the pipes. And remember, I have my further remote flow control valves set to pressure drop control. That way, the system can be sized, and that way the simulation can run and not hit the reference pressure issue. Okay, so now to go through this step by step. So I built the model. I have started with a placeholder pipe size. First thing is I need to turn on the automated sizing module. So we can do this by clicking on this button right here in the lower right corner of the interface. This opens up our analysis setup window, and it takes it straight to the modules panel where I can click on activate ANS. Now, let's talk about this thing here really quick. It brings on a new panel of things that you can look at for the automated sizing module. And this is a really helpful summary once you set up all of your sizing parameters. And so after you finish everything, you'll see a summary contained in here. So when you turn on the ANS module, this exclamation point means that you need to do something before you can run your model. As you notice, I have a red status light. So I have to set stuff up before I can run the model, which is fine. We'll click OK. And now, when we go to the sizing process, again, everything is done on this sizing primary window tab. So I'll click on the sizing tab. And so let's break this down and talk about these panels in a little bit more depth. These are several panels where you will set up your various sizing parameters. And this is set up in a way where you can start with any of these panels however you want. If you wanted to start off with defining your design requirements first, you certainly can. There's nothing saying that you can't set up your sizing method first if you wanted to. All those are perfectly fine options. But it is helpful and logical to do this in a proceeding fashion from left to right. And so that's where we start with our sizing objective. Now, if you look closely, you can see that there's a little green check mark right here. That green check mark actually means that everything that is set up by default on this panel is actually completed. So really, you don't actually have to do anything on the sizing objective panel. That's because we have already set this for you. So as a default, we have set this up to where this will size your pipes for you, and it's going to size things based upon piping weight. The goal is to try and minimize your piping weight, and that is going to be the easiest way to size your pipes in your system. And so here we have three options: perform sizing, we have calculate weight, do not size, and then we have do not size at all. So it makes a little bit more sense to explain those three things if I change the objective to monetary cost. That makes it a little bit more clear. So let's say that I actually had cost information, dollar per foot for different diameters of pipe sizes. That's all that you need, something as simple as that. There is a bunch of stuff that you can do down here. I'm not going to talk about that right now, but here's what this means. If I chose monetary cost, we want to try and minimize the cost, right? Not maximize it. We want it to be minimized. So if I was to choose the sizing option, which is already chosen for you, this is going to size pipes in my model. Now, let's say that I chose the middle option, calculate cost, but do not size. Well, let's say that this design actually started from a previous plant that I worked on. And so I'm trying to design a brand new plant, and it's got different design requirements, but the layout is very similar, and I'm just going to start with this sizing as a beginning point, and then I'll start refining it further. Well, maybe it's not all 16-inch sizes. Maybe it's all the sizes from the previous job I was working on. Well, what I might want to do before I try the sizing process is I've got new cost information where the previous design was based upon costs from 5 years ago. Well, if I've got new cost information, I can build that in, and maybe I've got some new energy cost information, and I might want to simply calculate the cost of my previous design based upon current costs, but don't actually size anything. That's what this is doing right here. Calculate cost, do not size. Very similar to Fathom's standard cost calculation examples. So Fathom in itself can do cost calculations. If you go back into the help file and scroll down to the examples section, cost calculation is something that is part of standard Fathom. And there's a couple examples. There's cost calculation beginner, do that one first, and then there's plant cooling cost calculation. So if we were to look at this and just go to the final report, you would end up with a report that looks just like this, where you can see how much everything costs, but we're not sizing them automatically. It's just, here's what the sizes that we've specified are, here's how much it costs based upon that. Now, if I set this to do not size, then that's not even going to bother calculating the cost. This is just a regular Fathom run. Why might you want to do this? Well, you might have already set things up in all these other panels, but you don't want to delete that information. You just want to ignore it and do a regular hydraulic run. Well, that's where you can use do not size in that particular case. All right, so in this particular example here, I'm doing a perform sizing, I'm doing pipe weight, and I want to try and minimize it. So that's all set up by default. Next is to go on to the sizing assignments. So for the sizing assignments, this is where you have a list of all the pipes in the model. I have all 35 pipes, like I said before, and there's 4 options. So let me select all the pipes. So if we click on all, this now allows you to do something with these pipes that we have selected. The simplest thing is do not size the pipes at all, and do not bother to calculate their piping weight. So that's what they're set in by default. It's not going to try and change the pipe size. It's just going to use the 16-inch diameter pipes I already have. It's not going to change their pipe size, and it's not even going to calculate their piping weight. It's just a basic run. The next option to include them in the weight is where it's not going to change the 16-inch diameter pipe sizes for these pipes on the workspace, but it will calculate how much they weigh. So it's keeping whatever's there, but it's going to calculate how much they weigh. If you're doing a cost calculation, it would say sizing and cost options instead. And it would say include in cost instead of include in weight. The third option is to only include if the weight changes or if the pipe size changes. So let's say that I have my previous design right here, and I'm just looking for opportunities to see if it can find a better pipe size. Well, if it happens to find that, maybe there's a few pipes that, can find a different size that gives a better design, i.e. a lower piping weight, in that case, I want you to size those pipes and calculate their weight if their pipe size changes. Last but not least, always include in weight. So this will size all of these pipes and it will calculate their piping weight or their cost if you're doing monetary costs. So that's what that means. All right, again, when we do this, I have 35 independent sizes. What does this mean? Again, when I go back to the workspace here, I have 35 pipes on the workspace. And so if I don't enforce commonality in pipes that would make sense to have the same size, I might end up with 35 different pipe diameters throughout my model. That could lead to probably the best design that you would ever see, a very low piping weight potentially, but that'll drive your purchasing people insane. So that's where it's important to enforce some level of commonality. That way things just make more sense and it's a bit easier, of a design. So I'm going to minimize my quick access panel and I'm going to move my sizing panel. I'm just clicking the tab and dragging it to this compass here and putting it on the right. That way I can see both windows. If you have dual monitors, then you can click and drag it onto its own screen, and that makes it a little bit easier because then I wouldn't have to scroll over to the right to see my common size groups. So when you want to enforce a level of commonality, for example, I want all of these pipe sizes to be sized, but then I want them to be the same size. That's our common size group. So the way that you create them is you simply click on New to create a new common size group. So I'm going to start off with the main header, and then I'm going to do the pump A piping, followed by pump B piping, pump C piping. When you are blessed with a system that has a really good level of symmetry, this makes it really easy. HXA piping, HXB piping, HXC piping, and last but not least, HXD piping. And oops, I spelled that wrong, so we can go back and we can actually rename it. So I'm going to right click and I'm going to say rename this, and we're going to put a G on the end. There we go, because that'll drive my OCD nuts. So again, how do we get all of these pipes into these different common size groups? Again, select them on the workspace first. A couple of selection tips. Yes, you can individually click on a pipe or a junction and hold the control key down, and you can select multiple things at the same time. But as you can see, it's really hard to click exactly right on these pipes. I miss it all the time, and I hate that. So that's why there's two selection methods that are really helpful. If I click and drag from left to right, you'll see that the box is a dotted black box. That will only select pipes or junctions that are completely in the box. If I click and drag from right to left, you'll see how the box is yellow. That will also select pipes or junctions that are crossing the boundaries of the box. So this is left to right. This is right to left. It gets more pipes in that way. So the way that I do this is I go from right to left for these pipes. Now I need to get these other two that are in the header as well. So I'm going to hold the control key down and then go from right to left again. And that's all there is to it. So now that they are selected on the workspace, I do have junctions selected as well. That's perfectly fine. It really does not matter. It doesn't impact anything. I'm going to click on workspace, and now that highlights those pipes that I've selected on the workspace. So now I'm going to go in to move to, and rather than clicking on the buttons individually, I'm going to click on the drop down, and I'm going to move all of these selected pipes to the main header. Now I already clicked on this area up here, this blue. I clicked right in here. That already sorted things by common size groups. So we can see that it's all set up to make it a little bit easier for me to read. Next, I'm going to select the pipes in the pump A piping. So I select them on the workspace and then click workspace, and then simply move to pump A piping. Now, if you wanted this entire stuff to be all the same size, you certainly can. But as you can see how I've defined my system, the splits do occur in slightly different ways. So the pumps are not exactly going to be operating in the same fashion. They'll be off maybe by a little bit. So the sizes might be slightly different depending on how different of hydraulics I have. Maybe I've got additional valves. As you can see, I have a elbow here in each of these paths, but not in this path. Also, if you're setting these T's to detail to where you're accounting for their losses, that will change things as well. So that's why I might want to allow each different path to be slightly different. So I select it on the workspace, move to pump B. But as we saw before, just because I have these as separate common size groups, they still might happen to end up with the same diameter. Now, that's not being forced, it's just how things work out. So now I do my heat exchanger path. So this is heat exchanger A. This is actually more pronounced because here we will see that we'll have different pipe diameters for the two different paths here for the parallel heat exchangers. They're operating in parallel. So that is a situation where, you know, if the hydraulics were exactly identical, then you might end up with the same sizing, but not always. Keep in mind, I'm forcing a flow of 1,400 gallons per minute through the heat exchanger A path, but for the flow control valve B, I don't have a fixed flow. So that flow is going to be whatever it is based upon a pressure drop of 10 psi. So that very well could cause my heat exchanger B path and D path to be different diameters. All right, so now I have all my common size groups set up, and I've sorted them by common size group. Now, one thing I did skip when I did this is it's good to get a sanity check to make sure you set things up right. So if I go back to the workspace, you can click on the view menu and then go down to color common size groups. And I'm going to color code all the common size groups. This is really helpful to do because this makes it really easy to see, oh, I forgot some pipes, or maybe I put things in the wrong group. So putting the color coding here on the workspace is really helpful once you get your common size groups all set up. All right, so now that our common size groups are all set up and our pipes are set to be sized, now we move on to the candidate sets again. So this is where, in order for our pipes to be sized, we have to select them from a specific list of available materials. In my example here, I'm only considering steel pipe. And again, only from 1 inch to 36 inches in diameter. So here we have a whole list of materials. This does not have a list of all pipe materials known to man. If you have your own pipe material that you have used that we don't have in here, you could very easily create your own custom pipe material library. Once you do, you will then see it in this list and you can choose from it. Now, things can be sorted in two different ways. The old-fashioned way was to sort everything by size. This wasn't really helpful because it would put everything for 1 inch and all the schedules. A lot of times it's much more helpful to sort everything by type or schedule or class instead. So here, I'm going to only consider standard schedule. So if you expand it, you can see here's all the pipe sizes for standard schedule. Here's all the pipe sizes available for schedule 10. As you can see, it doesn't have anything more than 36 inches diameter for schedule 10. So I'm going to select the schedule level, not the individual sizes, the schedule level, and then click add. That puts everything over there a lot easier for me. And then again, you don't have to delete things from this list. I'm just doing this to show you the flexibility, because that way it limits how many pipe sizes it's going to consider. Now, if you wanted to include other schedules here in this list, you certainly can, or you can do it as a separate candidate set. So what I can do is I can set this to where it's a standard schedule. I could create a new one and call this, schedule 40 options. And I can do that as well. You don't have to, but it's available. Now, you can do the same thing with different materials. You don't have to do only steel. If you wanted to include copper pipe, iron pipe, PVC, maybe you have a really, really complicated system where some pipes have to be HDPE, others have to be PVC, others might have to be steel for whatever crazy reason. You can have, excuse me, you can have different candidate sets because different common size groups might require different materials. So maybe the pump piping might require steel, where the heat exchanger piping might require copper for whatever crazy reason. That's where you can have multiple candidate sets if you want. In my case, I'm keeping it simple. I only have one candidate set. I'm going to select all the common size groups and the pipes that are not in a group, and I'm going to assign my candidate set to all of these material, or all these common size groups. So this means that when each of these groups are being sized, they can only choose from this particular list of materials. It can't go outside those boundaries. It can't just, right now this is only considering standard schedule. It cannot just magically all of a sudden try schedule 10. If you wanted to try schedule 10, you have to put that in the list as well. Okay, design requirements. This is what drives a design. So I'm going to click on new, and this is going to be my heat exchanger A and B. I need to put 1400 GPM heat exchanger A and B min flow. Set the as you can see, there are several parameters that you can set it to. This is going to be volumetric flow rate. Minimum flow is 1400 gallons per minute. Now I know that I'm at the top of the hour, so for those of you that are able to stick with me, I'm going to keep going. If you have to head out, thank you very much for listening in. Feel free to bounce out and enjoy your rest of your day. You will receive a link to the webinar. So if you want to pick back up on the recording and watch the rest of it, you can start right around 11 a.m. my time, and you can watch the rest of the webinar at your leisure. So I'm going to keep on going here. So I've got this, and I'm going to select that road. I'm going to duplicate it because, again, my second design alert is very similar. GPM, HX, C, and D min flow. And all I need to do is change the number. That makes it a lot easier. Then lastly, I've got a third design requirement, 10 PSI D minimum pressure drop. No, that's wrong. 10 feet per second max velocity. I'm jumping ahead of myself. So we got the velocity maximum is 10 feet. Again, if I did not put a velocity requirement here, the ANS module can size things to where, yes, I will get my minimum or my minimum flows that I want, but they can be very small sizes with really high velocities. That's going to require extremely massive pump energy requirements, and that's going to be very, very costly. We want to avoid that. So this is the beautiful thing about sizing based upon pipe weight is because it kind of gives you the best of both worlds. It's going to try and minimize your piping weight when it's meeting these flow rates, but it's only going to do it such that you have a maximum velocity. So it's going to drive your piping size smaller and smaller, but only to a certain point. That way, you still kind of get the effect of minimizing your system based upon your pump energy costs, if you were to consider that. So that makes it really helpful there. All right. So again, heat exchanger A and B is going to use this design requirement for these common size groups. And again, if you click on these boxes, it checks the boxes for all of the pipes in that common size group. So that really helps reduce a lot of clicks that you have to do. And then every pipe here is going to make use of the 10 feet per second maximum velocity. Next is my control valve design requirement. So this is 10 PSI minimum DP. Oh, 1 second. Excuse me. And so we're going to set our, as you can see, pressure drop is not the only parameter. Maybe you want to set this by open percentage if you like, or margin above vapor pressure. Lots of options are available for you. So minimum is 10 PSI. And again, I only need to check the boxes for flow control valves A and C. The reason why is because B and D are already set to a constant pressure drop of 10 PSI at the minimum. So you don't have to do that. Design requirements are all set up. Now, sizing method. Now, before, I just said suggest best method and use that as a starting point. These are all very sophisticated mathematical algorithms that are highly complex that will powerfully change your pipe sizes for you using gradient methods. So the easiest thing to do is to allow ANS to tell you, it looks at the model and it figures out which one might be the best method. Now that doesn't mean that that's actually the best method. As we saw before, this generated a piping weight of 245,000 pounds versus if I chose genetic algorithm and then started with a continuous method of modified method of feasible directions, this saves me 5,000 pounds, you know? So just because the suggested best method is chosen, that doesn't mean it's going to give you the best design. So my point is to look at all of them, try all of them, do each sizing method in a different scenario. That way you can easily compare which ones give you better options and whatnot. Also, stick with the default parameters here. That way it works as intended. You can go in and manipulate this all you want, but I would highly recommend that you really fully understand all of these methods and really read the help files to know what you're doing. Because if you set this up and change the values, you can very well not have good convergence or correct results. So keep the default values, but there are some parameters that you can go and tweak later on. I would say if you're starting with a particular method and you can't get convergence, don't jump to this stuff. Try another method first. Okay, so I'm going to go to the one that I know has the best results. And what we're going to do after this gives our sizing is we're going to take a step further and we're going to find a pump curve that will meet all of our sizing requirements. So here, initial design of 16 inches did not meet our design requirements, so that was infeasible. The continuous cost option was using any hydraulic diameter, 4.7 inches. That found convergence, and the best pipe weight was 216,000 pounds. Now it's doing the discrete sizing. So that's where the discrete sizing is only considering pipe sizes that are specifically listed in your candidate sets. It's not going to select any other pipe size in that case. And it's dialing in here and an answer here pretty quick. This is the best cost, and it's trying to tweak those pipe sizes further and further. And it takes just under about a minute and a half for it to get convergence based upon this mathematical method. In addition to how different mathematical methods can potentially give you different results for different pipe sizes and different resulting piping weights or monetary costs, the starting pipe sizes that you use can also have an impact on your final result. So if I started using 8-inch in diameter for the pipe sizes, that could make an impact on my resulting piping weight for the cost report, as well as the final pipe sizes. Okay, so here's our cost report. Same thing we got before, 241,000 pounds. Here's all of our pipe sizes. Here's our design requirements that shows that they've been satisfied. And so I'm not going to go into talking about what the colors mean right now. You can read through our documentation and learn more about that. It's contained in our ANS Quick Start guide. There is a separate ANS Quick Start guide that's available, and it talks about it there. So I'm not going to go into the different colors, but ultimately all of our design requirements have been met. And again, here's our visual report that you can choose which parameters you want to display. And I want to see if there's a, let's see, looking for piping weight. let's see. So here we have original pipe cost or value, and then we have sized pipe cost or value. So this is helpful also because here you can show what the original cost was based upon the original pipe size, which in my case was 16 inches in diameter. And here's what the new cost is based upon the actual pipe size that it uses. So those are some new parameters. Now look here that we see 8 inches in diameter and 10 inches in diameter. The reason for that is because we're not forcing the same flow through each control valve path right now. This is getting the minimum 1,400 gallons per minute, but based upon the sizing, this is getting almost 1,800 gallons per minute. And so that's what happens when we set this to a fixed pressure drop of 10 psi. So the flow split is very different. Here's how my pumps are performing, but here's our flow split through each heat exchanger. So later, what we're going to do is now I'm going to set my pipe sizes to input. So I'm going to call this sized pipes. And I'm going to click my thumbtack, and we will reload the scenario. And so now we can see that we've got all the pipe sizes. This is a case where now I'm going to go back into the sizing panel, and I'm going to set this to do not size. So here, I don't want to delete any of the information that I've set there. I just want to ignore it. So this is just doing a Fathom run, but it's still going to make sure that all of my design requirements are satisfied. So here, I'm just writing this. It's going to give the same exact results. All I'm doing is I'm setting things up so that way now I can find a pump curve. So here, I want to find a pump curve that meets these requirements. So the way that we do that is by clicking on this pump with a spark on it. And I'm going to use pump A as a reference. You can do individual curves for each A, B, and C, but ultimately you don't want to do that. You want to have them all be the same pump curve. So pick whichever one in this list that you want to use as a reference, and then you can size things based upon that. So I'm going to use the internet to find me a pump curve from a manufacturer. And here's my list of manufacturers. Just to keep things simple, I'm going to go with Berkeley and click on this button here to accept the things. So here's my operating point that gets brought in right from Fathom. So I click on next, and then I'm going to choose a product line. I'm just going to click on all of them to make it easy. And then I'm going to turn on more rows. And so my design requirement is 2,000 gallons per minute for each pump. So here I'm going to sort everything by proximity to the best efficiency point, because I want to make sure that my design flow rate is operating as close to the BEP for that specific pump as possible. So when I scroll down, I find that this pump right here is probably going to be my best option. Now you can download other options if you want as well. I'm just going to do one of them, and I'm going to download this IQX file. And this IQX file is what we need to bring into Fathom. So I'm going to put this onto my desktop so it's easier to find. I already have one there, which sounds good. So now I go into step 2. I'm going to open the file, which is this guy right here. And I'm going to apply that pump data to all the pumps on the workspace. So I've got sized pipes and pump curves. Now, if you were trying different pump options, I wouldn't want to put a pump curve in this scenario. I would probably want to create, pump option number 1, pump option number 2, pump option number 3. And then in these scenarios, that's where I would put different pump curves in. So I wouldn't necessarily do it in the parent scenario. But right now I'm only considering one option, so that's fine. So we can see that we've got our head curve, MPSH curve, and the efficiency curve. All that looks good. So now I can rerun my model, and this is going to give very similar results that I had before, operating very closely to 2,000 gallons per minute with the pump curve, but we still see that we have a really large flow split between each of the heat exchangers. So once you get pump curves in, now we can go back and set our original control valves back to flow control. So that's 1,400 gallons per minute, and this is going to be 1,300 gallons per minute. So now when we rerun this, if I need to make sure I have very close to the exact same flow rate through each heat exchanger, you can see that the pumps are going to operate further back on their curves. And so they're at about 90% of their BEP in that case, which is fine. That's still really, really good. And I have some decent MPSH margin right there. We can see here that we are getting exactly what, oh, I forgot something. Now this is where I would go back to sizing, and I would now choose the minimum DP for control valves B and D. So again, that's the beautiful thing about do not size, where it ignores everything, but it will still account for your design requirements. And this will tell you if any of your control valves had a lower pressure drop than 10 PSI, it would give you warning messages. So here, when we look at the pressure drop across our control valves, look at this. We have 23 PSI versus 28 PSI for control valves B and D. So because we have slightly different sizes on the secondary flow paths right here, we are going to require a little bit different of a pressure drop in order to get our design requirements in place, because they are using a slightly different size. Now, if you really wanted to refine things further, now that we have a real pump curve and we have our control valves set to their fixed values, you could go back in and say resize with FCVs and chosen pump curve. So this is where you can refine your design a little bit further now, because in this scenario, I could go back to sizing and say perform sizing. This is going to keep everything as it was before, sizing all the pipes, all the common size groups, all my candidate sets, all my design requirements. But now I'm just going to try and see, based upon my actual pump curves, and now that I'm using flow control valves, can this give me a slightly better design? And this is where, again, you would start with one particular method, calculate what the resulting piping weight is, and then compare it to the other options, and then go with the best one. Now, the best may not always be the best. You might end up with a situation where one of these methods gives you the lowest piping weight, but maybe you end up with NPSH issues on your pumps, because perhaps it does give you smaller pipe sizes. Well, what's that going to do? Smaller pipe sizes is going to make our velocities go up and our pressure drops are going to go up. That's going to affect the MPSH available for your pumps, because you've got higher frictional losses. So you would potentially end up with less margin in that case. So just because you have a better cost or a better piping weight that you find doesn't mean that it actually is. Other things need to be considered as well. Okay, well, thank you very much, everyone, for sticking around with me. That's all I'm going to demonstrate for today. If any of you want to take the automated network sizing module for a spin and try it out for yourself, feel free to contact us. If you're within the United States, you can contact me directly, Ben Keyser, and my email is benkeyser@aft.com. I'll type it out for you here. It's benkeyser@aft.com. You can email me, and I'll be happy to arrange a evaluation license for you for the automated network sizing module. If you are outside the United States, then please contact your local channel partner, and they will be happy to arrange a evaluation license for you as well. And you can find your local channel partner by going to our website, aft.com. Under the channel partners area, go to channel partner locations, and then whichever country you are in, then that is the channel partner that you can use. If you're in a country that doesn't have a channel partner, then you can contact us directly and we can help guide you, because some of these channel partners cross some international boundaries that represent multiple countries. All right. Thank you very much for your time today. And if you have any questions, let us know. And hope that every one of you has an excellent rest of your week. Take care, everybody, and have a great day. Bye-bye.